Well, all right. So now, officially, welcome back to day 2. So we got a lot of ground to cover today, and in the next 2 days after that. Day 1 was kind of just getting us all up to speed, getting us on an even keel, everyone at the same level. And now, bam, we're taking off. We've got an awful lot to do. So I'm going to start by quickly reviewing the material that we covered on the first day, and then moving on to some new stuff. Today, I hope we're going to tackle temporal autocorrelation, which truly is the bugbear that lies in the deep, dark cave that is bold fMRI data analysis. And we're going to then talk about 1/f noise modeling, temporal smoothing. These are topics that are often of some confusion to people who are starting off in the analysis of this data. And we're going to cover covariates of no interest. That should be a gentle respite from the confusion that is temporal autocorrelation. But then we're going to really get into experimental design then and start talking about sort of blocked versus event-related and how you optimally time events to design your experiment. Okay, so a fair bit to go over. But first, let's just quickly review with what with where we've been. So on our first day, we talked a little bit about the physics and physiology of bold fMRI data, pretty briefly, but we just went over the fact that bold fMRI data amounts to essentially volumetric images over time, right? So you have a volume, a picture of the brain that you repeat multiple times over the period of a scan. Each image you acquire about every 2 seconds apart, and each image is composed of 16 to 20,000 little voxels or volume elements, which are about 3 millimeters on a side. And we further saw how there's some chain of events that links changes in neural activity to changes in bold fMRI signal. And that chain of events includes such things as change in the local vasculature and changes of concentration of deoxyhemoglobin, which affects local static field or local magnetic field inhomogeneities, and then subsequently the bold fMRI signal. And we saw that despite all this complicated chain of events, that step between neural activity and bold fMRI signal can be summarized by reference to a linear system, okay? And we talked a little bit about how a system is something that takes input and gives output, and a linear system is a particular type of system that has some very nice properties. That among them is that if you double the size of the input, you get twice as much output. That if you give the same input one time and the same input a different time later on, that you'll always get the same output, and that the adding together inputs will give you the same outputs added together, okay? So all these different properties of a linear system, but that most fundamentally of all, if you know a property of a linear system called the impulse response function, which is the response of the system to a brief, very intense input, okay, then you'll be able to characterize the output of that system to any arbitrary pattern of input, okay? And then finally, we saw how you could use that information to help design covariates in the setting of a general linear model analysis of bold fMRI data, okay? So let's pause here for a few moments and see, are there any questions about the material that we covered on the first day that you'd like to go over before we press on and move up to warp speed? It's all perfectly clear. Yeah?
I was just wondering, is it actually linear as in a straight line, or is it linear as in monotonic, and we just happen to know what the function is, so we can pretend it?
So the question regards, is the transformation from neural activity to bold signal linear, or is it kind of just more monotonic, or what's it like? So just so everyone's familiar with the terms, monotonic just means a function that's continuously increasing. So a monotonic function could look like this. Right, that would be a monotonic function. Every point that follows is larger than the point that preceded, okay? Whereas a strictly linear function is one that can be fully described, a curve or a function fully described by, y equals ax plus b, okay, where the data is equal to, it's your position along x times a scalar or a slope. So actually, it seems to be the case that it's pretty close to a linear system, okay? That is that if you double the neural activity input, you get, double the output. So it's pretty close to this. Now, of course, there are nonlinearities, as we talked about, so points at which this curve starts to not be linear. In fact, maybe down here at the bottom, it kind of drops off instead of continuing along smoothly, and that's one nonlinearity. Or it might saturate up here and not continue to rise. But at least for the vast range of physiologic evocations of neuronal activity that we study, the system is pretty close to linear, at least good enough that we can use it. We can make useful models with the assumption that it's a linear system. Okay, and you might notice actually that this little equation is quite similar to the general linear model. You recall the general linear model was the equation of the form y equals g beta plus e, right? And so this was the equation which is at the heart of parametric analyses of bold fMRI data. And as you recall, these are the data. These are the covariates or predictors or independent variables which we're using to model the data. these are the parameter estimates or beta values, right? And this is the error term. And these are the components then that make up a typical analysis of bold fMRI data. Yeah?
Regarding the beta values,
Yes.
or the scalar values, I was a little confused yesterday because you mentioned that that's how close you are to predicting that your curve, your prediction matches the data.
Mm-hmm.
So if you're really good, that beta value will be very small because no.
Well,
I was confused because I understood that beta value to be how far off you are from the real data. So if you're not
that's
far
the
off
E.
at all, it should be quite.
That's the E. So the error, or the residuals, that's how far, that's the difference between your best fit of the data and the data itself. Okay, so the E vector contains kind of the difference across your observations of the difference between your model, how good your model did, and the data itself. Okay, the beta values, as you recall, or perhaps I'll try and explain again, it was the amount of scaling, how much you had to stretch those covariates up or down to make them fit the data as best as you possibly could. Okay, so sometimes for some effects you might have to stretch them up real big to fit the data. Sometimes you might only need to stretch them up a little bit. Sometimes you might even have to kind of flip them around and make them negative. You'd have to have a negative beta value because neuronal activity actually decreased during a given experimental condition as opposed to increased. Okay, so this beta value is free to vary, but ultimately the statistical significance of your result is dictated by the ratio of the beta value to the E or error term.
So it can never be the case. I was getting hung up because I was thinking of a scalar value. The closer you are to predicting the data, the smaller the scalar value you need to use.
No, because effects can be different sizes. So as we, just to recreate this graph yesterday, so imagine you had the data from the donuts and bagels experiment. Here's the donut effect, or here's the bagel effect, here's the donut effect, bagel effect, donut effect, right? And you've got two covariates which are modeling this data, one which is your bagel covariate, which looks like this, and one which is your donut covariate, which looks like this. Okay? And you say, okay, well, so if these values range from 0 to 1 and these values range from 0 to 50, right, how much do I need to scale this up or down to be able to best fit this? Well, I'm going to have to multiply this vector by 25 or so to kind of get it to fit into there, whereas this covariate I'm going to have to multiply by about 50 to get it to fit in here. Follow that? Okay? So this thing, it needs to be like, stretched out 25 units. This needs to be stretched out 50 units. So the beta value on this is going to be 50. The beta value on this one is going to be 25. Okay? So bigger beta value here indicates larger effect. Does that follow? Okay, so the beta value is the magnitude of the effect. It's answering the question, how big was the difference between your condition and the other unmodeled baseline, this sort of baseline state. Okay?
What are the red and blue lines then? I mean, what are they plotting?
Like what is this red line?
Yeah, it's a function, I understand. But where do you get the amplitude of 0, 1? Is that just
It's arbitrary.
constantly is off, or is it?
Yeah, it's arbitrary. So you start off by saying, okay, I'm going to create a vector which is 0 everywhere, but it'll be 1 at the point where, in time, where I presented a picture of a bagel. So I presented a picture of a bagel here, I presented a picture of a bagel here. So it's 0 everywhere, and then it's just 1 there. And then same thing here, this was 0 everywhere, and then 1 here. And then, so then if you just convolve, right, as we explored yesterday, convolution is multiplication in Fourier space. If you convolve this initial representation of neural activity by the hemodynamic response function, what you get is then this line that's in red and in blue. And then these things are what then serve as the predictors in your model. Yeah?
So it's the size and shape of the HRF that make that, just the size it is and not humongous? Because I think, if I'm understanding what Sanjana was saying, why isn't one of those just 50 already?
Well, because a priori, before you did the experiment, you had no idea what the size of the effect was going to be. Right? So you start off by saying, well, okay, well, let's imagine that this region of the brain had 1 unit of response to bagels and no response to anything else. And then let's imagine a different scenario where this area of the brain had 1 unit of response to donuts and to nothing else. Okay? And then let's see how those models did. And then say, well, actually, as it turns out, it wasn't 1 unit of response to bagels, it was 25 units. And it wasn't 1 unit of response to donuts, it was 25 units, or 50 units. And it turns out that these scales are actually completely arbitrary, right? So if I wanted to, I could just scale this instead of from 0 to 1, I could scale it from 0 to 5. So this would be from 0 to 5, and this is from 0 to 5. These beta values now, instead of being 25 and 50, would now be 5 and 10. Okay?
Conversely, they could both be huge and you're scaling them down. I mean,
Yeah, right. It's completely arbitrary. What matters is the relative comparison between these two things. Okay? And then the error term, in effect, the error term gets scaled by sort of the magnitude of these things so that the mathematics all work out in the end. But just so you know, I mean, the only thing that's really important, actually, is that both of these curves have the same height. Okay? Both of these vectors are modeling the same size of effect. Because what that allows you to do then is say, OK, well, what was the difference between the bagel effect and the donut effect? If both of these covariates start off at the same height, differences between those beta values I can then attribute to differences in the size of the effect, differences in the data. Okay? What's that? Well, that was a gross oversimplification. The t statistic is proportional to beta divided by e. But it's a lot more than that. So just again to try and provide you with the intuition. And I promised I was only ever going to put one equation up on the board. So I've used up my one equation. Sorry. Right. So, but the important thing is to understand that where these covariates come from and how they're related ultimately to statistical values. Okay. All right. Well, let's imagine that we decided to do an experiment based upon the knowledge that we have so far. Okay. So we know that we know something about the filtering properties of the hemodynamic response function, right? So as you recall yesterday, when we went through the process of going through what convolution is like and how that works with the hemodynamic response function, at one point I graphed something that looked like this. So this is the power spectrum of the hemodynamic response function, right? Where these are low frequencies down here and high frequencies up here. This is the amplitude. And you recall that, remember when we wanted to do that convolution to kind of figure out what the bold fMRI signal would be to some pattern of neural activity input, what we did was we took the power spectrum of that neural activity and then we did a point-by-point multiplication with the power spectrum of the HRF, right? And what we found was that one property of the HRF is that it tends to pass through low frequencies and tends to attenuate high frequencies, okay? So slow changes in neuronal activity that take place will be well represented in the bold fMRI signal. But fast changes in neural activity, things that go up and down, up and down, up and down very quickly, will not be represented very well in the bold fMRI signal, right? Those will get kind of smushed out or attenuated by the sluggish hemodynamic response function, right? Everyone remember that? Okay. So with that knowledge, that would then kind of give you some information about what would be kind of the best sort of fMRI experimental design that you'd want to use, right? So knowing that very fast changes in neuronal activity don't get represented very well in the bold fMRI signal, and remember, your whole goal here is to detect a change in the bold fMRI signal. So knowing that fast changes don't turn up there, maybe then what we should do is design our fMRI experiments so that they're predominated by slow changes in neuronal activity, right? So for example, if you want to find the area of the brain that responds to flashing lights, you might decide to do like 2 minutes of lights flashing on, and then 2 minutes of darkness, and then 2 minutes of lights flashing on, and then 2 minutes of darkness, so that these are very slow, these are relatively very slow changes in neuronal activity, right? Area of the brain is very quiet, and then it's active for a while, and then it's quiet, right? So very slow changes. These would be changes that are happening in a frequency representation kind of down here, right? So that if you looked at, if this was sort of a representation of the lights that you have in the room, right? Darkness, lights on, and these are, say, let's make it 1 minute each, right? If you take a look at the bold fMRI signal that we would predict as a consequence of having this pattern of neuronal activity, it would look very much like this. So it'd just be slightly kind of smoothed out, right? Just slightly smoothed out at the edges. But really, this fundamental harmonic of sort of this low frequency stuff would be very well represented, okay? Is everybody with me on that? Any questions about this so far? Okay, so if that's all you know about bold fMRI, so if you were to leave right now, catch the next bus back to wherever, and then start doing your fMRI experiments, then this is how you would design your fMRI experiment. So like, how would this turn out? So let's say we do this. So we're going to do an experiment. We're interested again in, I don't know, the effect of semantic judgments using pictures versus semantic judgments using, Braille reading or something, right? So you have some experiment, And for 60 seconds, they do one task, semantic judgments using pictures. And for 60 seconds, they do this other task, semantic judgments using Braille, Braille reading. And what you want to do is you want to see, are there areas in the brain where there's a difference in neuronal activity between making semantic judgments using one sort of material and making semantic judgments using another sort of material, okay? So, you're a big-time, faculty member at this point, so you got a big staff. So you grab, your best graduates and you say, like, okay, let's put this experiment together. Here's a big wad of cash for you to spend on scanning. Go on down to the scanner, collect 10 subjects worth of data with 60 seconds of semantic judgments of this type versus 60 seconds of semantic judgments of that type, and analyze the data in the manner that we've talked about so far, because we all attended Jeff's course, so we know what to do, and then bring back the results to me. Okay, great. So some time passes. Your Crackerjack graduate student comes on back and says, okay, here are the results. So here's subject number 1, and here's a picture of their brain. And what I did was I made this model of neuronal activity. So I said, let's imagine there's an area of the brain where there's more neuronal activity while you're making these sorts of semantic judgments, and less neuronal activity while you're making these sorts of semantic judgments. And then I had this as a covariate in my G matrix. And then I went and I looked at every voxel in the brain, and I said, okay, is there a significant relationship between the change in the bold fMRI signal over time in that voxel and then this predictor of what the signal might look like if it did have a difference between the two? And then I made this statistical map where at each point in the brain, I said, okay, well, let's take a look at the t-value. And if the t-value is bigger than 1.65, say, I'll put a red dot. Okay, so they come up with a map that looks like this. Okay, so there's red dots all over the brain. Red dots all over the brain. And they say, look, eureka, I found that most of the brain responds with a greater response to semantic judgments about Braille reading as opposed to semantic judgments about pictures. Okay, so now you, as the world-weary faculty member, what's your objection to what's been done so far? Someone's got to raise their hand, or I'm going to start calling on you.
Too many dots.
What do you mean, too many dots?
Well, you don't. There. First reaction. You haven't discriminated between 60 seconds is I think a long time for doing one task and switch to another task. You don't know if during one task versus the other task are doing the same thing.
Okay, so you're making an objection on a fairly sophisticated level to the experimental design, the notion of trying to, the cognitive process of semantic judgments over these periods of time, stuff like that. Let's hold that idea. How about just purely from a mathematical standpoint? I took this statistical map. It's got 20,000 voxels in it. In each voxel, I threshold, and I said, put a red dot there if the t was greater than 1.65, which corresponds to a p equals 0.05. Where's bond for anyone you need him? Could you please explain bond for any correction to the audience? So what's your objection?
Well, if you run enough comparisons, sooner or later you'll hit.
Right. Okay. So let's suppose that in one voxel, okay, I set the threshold to be t greater than 1.65. Only kind of color this voxel red if the t was greater than 1.65, which corresponds to a p-value of 0.05. And as you guys know, a p-value means that's the significance or the chance that you would have gotten this t statistic just by like random fluctuation in the noise. Okay. And so p 0.05 means about 1 in 20 times or so, this voxel would have had a significant effect in it, greater than 1.65, just even if there was no difference between these two different conditions. Okay? So, all right, well, I'm not dealing with 20 voxels. I'm dealing with 20,000 voxels. All right? So if I have a threshold of 1.65 for each of my 20,000 voxels, then there's going to be an enormous number of these voxels which are going to have a significant effect in them just by random chance, right? Just the random fluctuation of the noise is going to happen to look a little bit bigger during semantic judgments about Braille reading than semantic judgments during the other sorts of things. So this is wrong. So obviously I need a higher threshold here to kind of correct for the fact that there's 20,000 little voxels that I'm comparing for. So, whatever, I'm a sophisticated analyzer of bold fMRI data. I do some sort of correction, which we're going to talk about a little bit more on day 3. And so I now say the t has to be greater than 4.7. This corrects for, take my word for it, corrects for the number of voxels that I'm comparing for. Okay? So now what I'm suggesting is that the chance of there being even just one voxel as a false positive in this map of greater than 4.7, I'm saying that even the chance of there being just one voxel is now 0.05. Right? So only 1 in 20 times should this map have even a single voxel in it by chance. But nonetheless, there's a couple of big blobs here that survive the comparison. All right, call nature, right? We got a cover story here. It's going to be like the difference between semantic Braille reading and picture reading. I'm all set, right? Well, so you're writing up the paper, you're getting the figures all together, and then your graduate student comes in and makes a fairly sheepish confession. They say, well, you know, I didn't really want to tell you this before, but we ran into some technical problems. Actually, the projector that we were using to present the stimuli down in the scanner, the bulb actually burned out on the first day. So I've collected 10 subjects worth of data, but actually the 10 subjects were just sitting in the dark the whole hour worth of scanning. They didn't see any stimuli whatsoever, right? It was completely dark. They didn't see any. There was no difference. There was no, you know, braille reading. There was no picture judgment. They just sat in the dark for the whole 10 minutes. Yeah, well, you know, there's a problem with that thing too. Thanks very much. Yeah, we could use you, you know. So in any event, right, so there was no stimuli whatsoever. The subject just sat in the dark for the whole hour worth of scanning. So what the hell happened? So how come it is that I have all these significant blobs, even though the subjects did nothing, right? So in effect, these were data that were collected under the null hypothesis, right? Because since I didn't present any stimuli, there really shouldn't be any difference between, you know, this one condition and the other condition because no information was presented to the subject whatsoever. So this is what's referred to as the null hypothesis. That is, I would expect it to be the case that there should be no difference between these two alleged conditions. Yet nonetheless, there it is. There's a difference, a statistical significant difference in this map, even though there was no stimuli presented. So what could this be? All right, so step one to trying to figure this out is you go and you start taking a look at the data from any one voxel in the brain. So you just plot the data. So you say, okay, well, let's just pick a voxel here, or even let's just pick a voxel in here. And let's make a graph. And we're just going to plot the data over time. So this is just time. And this is the, you know, the magnitude of the signal. So this is bold, you know, just the bold fMRI signal over time from that voxel. Okay, and it looks something like this. Right? Say, okay. And so now you pick another voxel. So what's that voxel there look like? And you plot that one, and it looks like this. Like that, okay? And so on. And so you say, okay, well, let's see. There seems to be like an awful lot of kind of wavy up and down kind of stuff, and there's also like some big like linear drifts where the signal seems to be either rising or falling over the course of the scan, okay? So you say, all right, well, what's another way that I could try and interpret this? Well, let's take a look at the power spectrum. So we're kind of used to looking at power spectrums. Now let's look at the power spectrum of each one of these voxels, okay? The time series data from each one of these voxels. So what would that look like? So this is now low frequencies, high frequencies. This is now amplitude. Okay, and this is a power spectrum of the data from any one voxel over time. And what you find is it looks a little something like this. In fact, if you took the power spectrum from every voxel in the brain and averaged them all together, right? So you say take the power spectrum from this voxel and then add it to the power spectrum of this voxel and add it to the power spectrum of this voxel, add them all together and average them out, you get something that looks like this. So you say, that's kind of funny. So what do I know about power spectrums and noise and the null hypothesis? Okay, well, let's see. You know, in most systems, in most kinds of things that scientists study, if there is no effect, okay, if it's under the null hypothesis, we expect that the power spectrum is going to be like white noise. Okay, so you guys know, like, if you turn your TV to channel, I don't know, 22 or some channel which does not actually broadcast, you get like that white flickering noise, right? For those of us who don't have cable like me, that's what I see on most of my channels. Okay, so if you look at that, that's white noise. It's random thermal noise. And so white noise has the property of that it has the same amount of power at all different frequencies. In fact, that's why it's called white noise. Okay, because you guys know that light, right? The visible light spectrum is a spectrum. Okay, which has different frequencies with, like, you know, light of fast frequencies with small wavelengths and longer wavelengths. Okay, and that white light is a combination of, you know, red and yellow and blue and green and indigo and violet and all the rest, all equal proportions. That's what gives you white light. Well, white noise is where you have equal power at all different frequencies. So the power spectrum of white noise should look like that. Okay, a flat line, equal power at all frequencies. Okay, and that's under most experimental circumstances. If you look at your data under the null hypothesis, that's what you should see, white noise. In fact, that's the most parametric, in fact, all parametric and most non-parametric statistics assume that this is the case. This is such a fundamental property of data that just about every statistic that we use makes this assumption that the noise under the null hypothesis has this property, that it's white noise. Okay? But our data is manifestly not white. Okay? In fact, it's pink. So if you were to take this power spectrum and kind of turn it into colors, This would be pink noise. That is, it's more red than anything else. Okay, pink noise. In fact, pink noise also goes by another name. It's called 1 over x noise. And the reason that is because a function that kind of fits this pretty well is a 1 over x function. It's exponentially increasing as you go to lower and lower frequencies. Oh, heck, that's an equation. Sorry. So in any event, but in our parlance around here, we tend to call this 1 over f noise. And the reason we call it 1 over f is because it's 1 over frequency, right? The power of the noise increases as you get to lower and lower and lower frequencies. Okay. So what's this doing? Well, the property of having noise like this is that if you create an experiment that's looking for like low frequency, slow changes in neuronal activity in your bold fMRI signal, you're going to find it, right? Even if the graduate student doesn't turn on the stimuli, you're going to find slow changes in neuronal activity in your experiment, okay? Because there's an awful lot of, what's that? Oh, it's always the graduate student's fault. So there are slow changes of signal rising and falling within the bold fMRI data, okay? Just all on its own, just someone resting quietly in the scanner. In fact, you know what? People ask, well, where does this 1 over f noise come from? Maybe it's, so people you look in the literature, frequency noise, 1 over frequency noise, what is that stuff? We'll find that all sorts of complex systems have 1 over f noise, right? So the collision of galaxies and bidding on the stock exchange, all sorts of things have like 1 over f noise properties. And people say, oh, maybe the brain's a complex system, and people are thinking, and there's thoughts racing back and forth, and that's why there's 1 over frequency. Well, sorry, actually, if you just take a jug of water, a plain old jug of water, a spherical phantom, and put it in the scanner and collect bold fMRI data, you will see 1 over f noise. Okay? If you put it, yes, it's been done. If you put a cadaver in the scanner, which has been done, and collect bold fMRI data, you will see 1 over f noise. Okay? It's just a fundamental property of bold fMRI data and the way it's collected in the operation of the scanner. I don't really understand why it results from the operation of the scanner the way it does, but it is ubiquitous. Okay, any scanner anywhere that uses bold fMRI is going to have 1 over f noise in it. It varies in amplitude and severity from location to location, and the truth is it is goosed up a little bit by having a human subject in there as opposed to a jug of water. But it's a fundamental property of the scanner. Okay, and it is completely ubiquitous. And you'll also hear the explanation every once in a while that all this stuff is just this is just physiologic noise, cardiac rhythms like the heart beating and people breathing, and all right, maybe a little bit of it is, but most of it is just fundamental properties of the scanner. It's unavoidable and irreducible. All right.
But it's gonna be like all scattered around over the whole brain, not like that.
Mm-hmm.
Only flat.
Right. So is it the case that some areas of the brain have more 1 over f noise and other areas of the brain? Yes. And in fact, let me start by saying this is a very irritating property of bold fMRI data. It is very irritating because it means then that all the traditional statistics that one might use to analyze data are no good. Okay? And it also produces all sorts of complications for designing fMRI experiments, which we'll talk about in just a moment. So it's irritating to begin with. And if that weren't irritating enough, it is highly variable in its shape from voxel to voxel across the brain, okay? Particularly in its low frequency components. So if I plot the power spectrum, not all averaged together here across all the voxels, but now show you not only what the average power spectrum looks like across the voxels, but also its standard deviation as a function of frequency, it looks a little bit like this. So the 1 over f frequency actually looks more like this. That is, there's a greater and greater spread. In fact, it's even more dramatic than I've drawn here. But there's a greater and greater spread of different possible curves at low frequencies as compared to high frequencies. So that is, the noise, the amount of low frequency noise is very variable at the low frequencies. Luckily, at the higher frequencies, it's a little bit more consistent. But at low frequencies, it's very variable. Okay? So this is yet another annoying property, because it means then that if we try and represent what the noise looks like across an entire brain, we're going to be systematically wrong. If we make one assumption about what the shape of the noise is like, we're going to be systematically wrong, because every voxel has a slightly different 1 over f noise property. Okay? And that assumption is worse and worse at lower frequencies as compared to higher frequencies. Okay? Yes? If you make a map of this, it doesn't really look like, it isn't anything consistent. It isn't, for example, like always the ventricles that have the 1 over, or always the gray matter, or always the white matter. There doesn't seem to be any clear tissue segmentation associated with it. There's definitely, let's see, areas of the brain like near the edges can have other superimposed noise as well from like movement and pulsatile artifacts and things like that. But in general, the 1 over f noise is not smoothly contained to different tissue compartments. It seems to be just,
It's not near
no, it's just everywhere. It's a real pain in the butt. In fact, there's, you can see heterogeneity even in water phantoms as well. So, okay. So 1 over f noise, this fundamental problem. So what are some consequences of 1 over f noise? Well, so number one, we know traditional parametric and non-parametric statistics are no good, because they give you results like this. Even if the subject did nothing in the scanner, you will find, and you assumed that they did some kind of like low frequency task, you will find something in the brain somewhere that correlates with the task that they didn't do, okay, which obviously is not something, not a property you want of a statistical test. A second consequence of the 1 over f noise is that it renders certain sorts of experimental designs less powerful than others. Namely, experimental designs that look for slow changes in neuronal activity are going to be rather tough to do because it's going to be hard to distinguish a slow change in neuronal activity that you introduce with your experiment from all the slow changes in bold fMRI signal that were there just as a consequence of noise. Okay? It's hard to distinguish experimentally induced slow changes in neuronal activity from noise. So that would suggest then that if you want to design like a pretty good bold fMRI experiment, you should aim for fairly high frequencies, right? The higher the frequency, the faster the repetition or on and off of neuronal activity, the better you're going to do from the standpoint of the 1 over f noise. But wait a minute. That's exactly the opposite of what I just told you with regard to the HRF, right? Remember, I told you that because of the filtering properties of the hemodynamic response function, you want to have an experiment that produces very slow changes in neuronal activity. And now only 5 minutes, I'm telling you, or perhaps 10, that because of the 1 over f noise function, you need to have experimental designs which have very high frequency alternations between them. Well, this would suggest perhaps that there exists a trade-off and maybe even an optimum between these two opposing forces, and that's indeed the case. In fact, if you know the shape of the hemodynamic response function and you know the shape of the 1 over f noise spectrum that's contained within the data, you have all the information you need to know to design optimal fMRI experiments. Okay? Optimal from the standpoint of maximizing power for detecting stuff. Okay? That's all the information you need to know. And we're going to talk about some different experimental designs in the next hour and 15 minutes. And part of the, or all of the claims that are made about the relative power of those different designs come from reference to knowledge of the shape of the HRF and the 1 over f noise model. Okay, any questions about this so far? Yeah?
This is just sort of a side issue, but is this, I've heard people talk about high field scanners, about how you get better signal without getting on noise. Is this 1 over f noise or
I don't know. I don't know, actually. There's a lot of challenges that come from scanning at very high field strengths, one of them being inhomogeneity of the, I think it's called the dielectric. I think is there a physicist in here? Or a radiologist masquerading as a physicist? So what is the challenge of very high field strength MR? There's something called the dielectric, which I don't really know what that is.
I guess maybe I'm not the best person to answer that, but certainly you have greater susceptibility to mineral and things like that, so there's more problems with susceptibility.
Mm-hmm.
The signal to noise is actually higher.
Right.
But I don't know. What do you think there?
Yeah, signal to noise is higher, but the susceptibility effect, which is partially driven down, other effects is higher.
Mm-hmm. Yeah, so in general, going to a higher field strength is better, but there are some greater technical challenges that accompany that. I don't think it's directly related to 1 over f. In fact, the 1 over f noise that we see on our spanking new 3T Siemens machine is less than we used to see on our 1.5T GE machine. Now, whether that is signal strength, or whether that's the strength of the magnet, or because Siemens is better than GE, or because the magnet's better shielded or better shimmed, I don't know. I just don't know. Because the fact is that nobody really fully, at least I've never seen anyone who has a credible explanation for sort of the full explanation of where 1 over f noise comes from. So I don't know yet kind of where it would come from or how you get rid of it.
So Jeff, you may have answered, or somebody else may have asked the question, is the 1 over f spectrum reflected outside the sample indicative of 1 over f noise in the sample?
So for example, could you measure, if you put a subject in the scanner and put like a water tube phantom next to their head, could you measure 1 over f noise from the water tube phantom and then know? Right. So this has been done. Dan Kimberg and I did experiments like this some years ago where we taped big jugs of water to people's head and put them in the scanner. And actually, our aim at that time was to try and model the global signal change, which we'll talk about in a moment. So, but it turns out the 1 over f noise in the water jug phantom is of a very similar shape to the same noise that you see in the tissue of the brain, although it's a little different in amplitude, so that the human brain tissue has a slightly increased 1 over f amplitude as compared to the water, but its shape, its inflection shape is the same. But disappointingly, the global signal fluctuation, which we'll talk about in a moment, is quite different between the water and the human brain tissue, which means that there's this other source of noise that we're going to talk about in a minute that you can't remove by doing that trick.
And the signal from the air, noise,
Noise, yeah, noise from the air.
that doesn't reflect the 1 over f?
You know, I've never looked at it. I've never looked at it. It's an interesting question. I mean, if the sort of the thermal noise that you see from just imaging of sort of outside of the brain reflected 1 over f, then that would further tell you something about its nature and kind of what it comes from. But I've never looked at that. So we should. That's a good idea. Okay. Yes.
So this 1 over f is the area of what you're measuring and not necessarily how fast you're measuring.
One more time now.
It's not, the error is not in the sampling rate, but in what you're actually measuring, the frequency changes of the actual response.
The thing is that, so let me try saying this. I don't know if I fully understand the question, so let me state it this way. So the 1 over f noise means that there are patterns of variation in the signal in bold fMRI data, which tend to have a lot of power at low frequencies. So there's a lot of, the bold fMRI signal is changing in a big way at slowly over time.
Does the error change depending on your TR?
Oh, does the error change depending on your TR? Not that much. So you'll see, if you go to very long TRs, the 1 over f noise continues to be there. So it's there for long TRs and short TRs as well. And again, there was some work that was done a few years back, I'm struggling to remember right now, which systematically looked at the patterns of noise at different TRs and with varying different imaging parameters, the echo time and all sorts of things like that, and TR repetition time. And it generally you could make modifications to the 1 over f noise, but it was again ubiquitous. It was present under all circumstances. And I don't remember precisely what it was that made it a little bit better or a little bit worse, but it had little practical consequence in the end. Okay, so I think in the end, 1 over f noise is sort of a reality of bold fMRI within subject data analysis that we just need to deal with. But as on the last day, I'm going to talk a little bit about perfusion fMRI, which actually is an imaging modality which escapes 1 over f noise for reasons that we'll go into in that time. Okay, so there's different ways that you could deal with this 1 over f noise that's present in fMRI data. Okay, and the way that is the primary technique adopted, at least in the SPM code that's out there and in VoxBo, is to try and model what that 1 over f noise looks like, and then have sort of this thing called the modified general linear model, which takes into account what the noise might be at different frequencies a priori. Okay, so in effect, it's a way of saying like, yo, general linear model, expect that you're going to see this kind of effect for low frequencies just under the null hypothesis. So then compare any experimental effect to this kind of changed baseline. Okay, so different software packages have different ways of doing this. In SPM, the main way that this is done is that SPM takes the average power spectrum across your data, right? So just as I showed you before, and fits a curve to it, an autoregressive function to it, and then uses that function to kind of basically let the model know what to expect. VoxBo does something very similar. We take the average of all the power spectra from the different voxels, and you get this representation. The one additional nuance is that, in addition to the noise, if you take the average power spectrum from an experiment which the subject actually did a task, so suppose every 30 seconds you flash lights and 30 seconds was dark, 30 seconds you flash light, 30 seconds was dark, you might see this noise power spectrum, but then superimposed on it a little blip here. So what would that be? Well, that's your experimental effect superimposed on top of the noise spectrum that was there to begin with, right? So you imagine that there was, to begin with, if you hadn't presented your stimuli, there was going to be a noise spectrum that looked like this. Okay, and now you flash light, so that increases neuronal activity in visual areas, and then decreases it, and increases it, and decreases it. So that's going to produce a fluctuation in the bold fMRI signal, which is reflected in this power spectrum. This is a power spectrum again: low, high, amplitude. And so these are basically the effect of your task. Is everybody with me on that? Anyone have a question about that? Okay. So what we do then, just for modeling purposes, we say, okay, well, ignore these frequencies. Fit a curve, but ignore these frequencies at which there was a task, so that we can fit the curve that was there, unmodified by the presence of experimental variance. Okay? Yes?
When you do this in Voxpo, what would you select the power spectrum from one scan to not really the average of the entire experiment?
Yeah, so what we do is we take the power spectrum from one scan and fit a curve to it. And then once we know the power spectrum from one scan, it's easy enough to kind of expand that out in time to say, like, this is what the power spectrum would look like over all the scans. If you wanted to, you could take the average of the power spectrum across your scans to get an even better estimate of the power spectrum, which would be, yeah, that would be a reasonable and appropriate thing to do. Yeah.
And also, does it make a big difference if you add those covariates? So I've been trying to adding the condition function curves.
Mm-hmm.
That and different, you get different results.
Well, you would expect the fit would be different depending upon whether or not you mask out these frequencies or not.
But is there any case where it would be better to not include it?
Yeah, so the case in which it would be better not to include it, we'll come to in a moment, and those are experimental designs which don't have their power at just one or two frequencies, but instead have power at all frequencies. We're coming to that, and I'll be sure to make a point of reminding you of that when we get to it. Okay. There are other things you can do. Other software packages try and whiten the data, which means effectively to deconvolve. I won't get into the details, but trying to basically take data and take away that 1 over f noise component, deconvolve it or remove it to what's called whitening the data to try and take it away. And there's benefits and drawbacks of both those things, but I'm just going to mention at least the top two kind of ways that this is done, both in SPM and in Voxpo. Yeah.
If you're modeling noise, though, doesn't it correlate with the power spectrum of the HRF?
Doesn't it correlate with the power spectrum of the HRF?
It looks like the noise is correlated with the signal.
One more time. It looks like what?
It looks like the noise is correlated with the signal.
It looks like the noise is. You mean is what you're saying? So are you making this observation that the 1 over f power spectrum looks a little bit like the HRF power spectrum? Yeah. Well, yeah. I mean, they're similar in that the HRF power spectrum passes low frequencies better than high frequencies, and the 1 over f power spectrum is such that it has more noise at low frequencies. Those two things are true.
Right, but then when you model it, how does the model know what part to attribute to the noise and what part to attribute to the signal?
Well, because those two things are not treated equivalently within the model. So the HRF, the role that the HRF plays is in designing your covariates, right, and creating covariates of different shapes. So it might be the case that the model says expect this much noise under the null hypothesis, okay? And then when you actually take a look at the power spectrum of your data, it might have, this kind of shape to it or appearance to it, okay? And then you have a covariate. These are now all power spectrum things. So here's the power spectrum of a covariate, and my power spectrum of the covariate might look like this. Okay, and so the model will say, all right, good. So that means that there was an effect of my task, which was, this unit big, right, as opposed to that big. Okay, that's the way that you can intuit that this is working. Saying, okay, well, the effect size here is scaled relative to the 1 over f noise baseline as opposed to some absolute baseline. Okay. All right. So.
Basically a variant on a low frequency filter.
What's done in the analysis? No, it's not exactly the same. Although we do apply a high pass filter in our analysis at a point, but it's a little bit different because even if, so for example, if this is the noise power spectrum, and then here are the task effects. If we just did a low pass filter, or I'm sorry, a high pass filter, which we actually do, and for reasons that I'll talk about in a moment, and say just kind of digitally filter the data so it looks like this, you still are stuck with having to take into account the decelerating function that you have up here. So it's not simply filtering. It's actually it's what the mathematicians call a sandwich estimator for modifying this general linear model to take into account this pattern of the noise. So it's not, unfortunately, completely characterized or taken care of by just digital filtering. There are these additional things that have to be done. All right, so let's talk for a moment then about filtering in the context of data analysis and all the rest. So we've established then that that fMRI noise has this property of having this 1 over f pattern, and that furthermore the variability of the noise is greater at low frequencies as compared to higher frequencies. Okay, and as a consequence, then we in our analysis of the data we fit a curve to the average power spectrum from the brain, and then use that to try and anticipate how much noise is going to be in the data under the null hypothesis. But as you'll recall, one thing I mentioned, a flaw of this approach is that by making the assumption that this is the shape of the noise across all of our analyses, we're going to be systematically wrong in that a lot of the voxels are going to have different patterns of noise from what we assume. Okay? And specifically, different voxels will have higher and lower low frequency noise just systematically. There's a lot more variability from voxel to voxel and how much noise there is at these low frequencies. Okay? So what that means is that our statistical model won't do as well in sort of making this correction for experimental designs that are at this very low frequency or correcting for this very low frequency. So that has led to the practice in the analysis of bold fMRI data of doing digital filtering to try and remove low frequencies from the experiment. Because these are not very, because number one, there's a lot of noise at those very low frequencies, and number two, we know we don't do a very good job of modeling them with these techniques that I've described so far. The safest thing to do is just to digitally remove them by filtering the data to kind of set the power at those low frequencies to 0. And just to give you a graphical intuition of what that looks like, so imagine this is your task. Imagine this is the effect that the true effect that's going to be present in your data. Okay, but the actual data that you record with the 1 over f noise superimposed looks a little bit more like this. Okay, where there's some low frequency component which is kind of superimposed that looks like this. There's also some sort of like slow drift that's increasing like this. But on top of it, there's your true effect that's there. Okay, if you do digital filtering to say remove these low frequency components from the signal, what you're left with is something that looks like this. Okay? So in effect, what you're doing is you're removing variance or variability in the data that's at sort of this very low frequency range. Okay? Now, of course, you don't want to remove the frequency that is your experiment itself, because then you'd just be left with this. Okay, which would be a mistake. So generally, what we do then is, in terms of a power spectrum, if there's the noise power spectrum and here's your task effects, right? What we'll do is we'll digitally filter all the frequencies which are below that of your task, so that it looks like that. Okay. So in SPM and in Voxpo and other software packages as well, typically there's a technique that exists for smoothing your data or filtering your data to remove low frequencies. Yes. Yeah.
When in the past one, and actually this experience is when we change on the filters, it doesn't change the data.
Doesn't change. You mean doesn't change your statistical results? Well, I mean it's possible that so I've drawn a fairly extreme example here, but depending upon the experimental frequency that you use, it could be that here's the 1 over f noise power spectrum, and here's your task up here, right? So it doesn't really make much difference if you filter to this point or this point. It won't have too much of an effect upon.
Do you have any rules of thumb for when filtering, what sort of tasks or
Yeah, yeah. So this is an area in desperate need of some rigorous guidelines, and unfortunately there aren't any right now. So here are at least a couple of rules of thumb. If you have a blocked fMRI experimental design, and we haven't even talked too much about different types of experimental designs, which we're going to do right after the break, but if you have a blocked fMRI experimental design, one in which you have sort of 30 seconds of this, 30 seconds of that, 30 seconds of this, 30 seconds of that, and that's a case in which your experimental variance is at a pretty low frequency, right? The neuronal activity you're interested in is 30 seconds here, 30 seconds there. All right, in that case then, most of your experimental variance is going to be concentrated at one of these low frequencies, right, down here. And in that case also, almost all of your experimental variance will be that frequency. So you can safely remove all the frequencies below that point without much trouble at all. Okay? In general, block designs are the ones that benefit the most from this kind of low frequency filtering. And the filtering, what you need to do for filtering for sort of event-related designs and randomized designs, which we'll talk about in a bit, is a little bit more complicated, and I'll try and address that as we go along. But at least the case for a blocked experimental design is quite clear. Yeah? Oh, sorry.
If you filter up right up to the frequency of the test, are you thinking about it to see something that
Ah, great question. Great question. So the question was, so wait a minute, if you're doing all this filtering, aren't you just going to kind of mold the signal to look like what it is you want to see? And it's absolutely true. I could take any pattern of noise, and if I filter it enough, I will make it look like exactly what I want to find. Okay? I could take this data and say, oh, I'll take a little bit of this sound, a little bit of this, and let's remove like these little high spiky things, and eventually, I can take it down to where it's a perfect representation of what I'm looking for. Okay? And so obviously, again, that's not a property that you want to have an honest statistical analysis of data. So what to do? Well, it turns out that, again, the statistical model we use is capable of taking into account the fact that you've done this smoothing. Okay? And the way that it does this, in effect, is by adjustment of something called the degrees of freedom. So degrees of freedom, for those of you who aren't familiar with the term from statistics, it's basically you earn 1 degree of freedom for each observation that you make in your data. So if you have a scan which has 1,000 TRs in it, right? You take 1,000 pictures of the brain, you've earned about 1,000 degrees of freedom. All right? And this represents the number of different ways in which your data can vary or assume different forms or shapes. Okay? And every time you try and model something in the data or take something out of the data, you spend some degrees of freedom. Okay? So if you remove some low frequencies, you have to spend degrees of freedom to do that. In fact, every frequency that you remove costs you 2 degrees of freedom. And so, and what's the consequence of spending degrees of freedom? Well, the fewer degrees of freedom you have, the less significant your statistical test is, right? So a t-statistic, a t-value of 1.65 is equal to a p of 0.05 if you have 100 degrees of freedom. Okay? But if you only have 5 degrees of freedom, that same t of 1.65 is now equal to a p of 0.27, much, much less significant. Okay? So the more degrees of freedom you have, the more significant your statistical results are, which is why you don't want to willy-nilly spend them. Okay? But nonetheless, since in fMRI experimental designs, we start off with an obscene number of degrees of freedom. So if you take these data, back in the old days when you would take these data to statisticians and say, like, hey, how should we analyze bold fMRI data, their jaws would drop open at the number of degrees of freedom you have. 1,000 degrees of freedom is a lot of data to start with. And so you can actually do a lot of filtering and manipulation and modeling of your data and still have a healthy number of degrees of freedom left for inference. But to answer your question, the way that we do account for the fact that we're shaping and sculpting the data is by making these adjustments. And what you can show is that you still maintain an unbiased statistical test at the end of the day, even after you do these things. Okay? Temporal filtering. This is let me tell you something. One over F noise and temporal filtering are definitely the hardest concepts to kind of get your head around when you're thinking about analyzing bold fMRI data. And it's the kind of thing that it just takes like time working with this stuff in the lab to really get it and to kind of see the explanation a few times. I suspect that when people decide to come back to this course, like 1 year after the next year, it's mostly because they still don't quite understand what this thing is about. Because it's a little complicated and rather counterintuitive. But we will return to this as a topic over the next couple of days and maybe tweak our understanding of it as we go. But at least that's the fundamentals that I wanted to introduce. Okay, let's take a break now. We've been at this for an hour. When we come on back, we're going to do covariates of